Okay, this month we're going to take a look at an introduction to coroutines that were added in C++20. This will not be a deep dive of every single little tweakable feature of coroutines. It's just going to be a gentle introduction so that next month we can talk about Boost Cobalt, which is a new library that makes it easier to work with coroutines and asynchronous code in general. So, what is first before we talk about coroutines, we need to talk about what is a subroutine. So, in C++, a subroutine is a function, so just a free function. Could be a C-style function, could be an overloaded function. It can be a lambda function, and remember that a lambda is just syntactic sugar for declaring a class with a function call operator method on the class, and just like the function call operator method on a lambda, a class can have any number of member functions. So all of those are considered subroutines, and you transfer execution to the subroutine by calling it, and when the function returns either by executing the last statement in the body of the function or with an explicit return statement, the execution returns to the caller. And to manage all this, the compiler creates what's called a stack frame. So this is a region of memory. It's almost always on the stack. And this is allocated by the compiler when a function is called. Strictly speaking, there's two ways of allocating this frame, whether the frame is allocated by the code generated for the function that is being called, or whether the compiler generates code in the caller before transferring control to the function. But the stack frame is a chunk of memory on the stack, and it contains enough space for the arguments to the function. And typically, local variables are created on the stack as well. Now, you can, have a local variable that represents data allocated on the heap, in which case the thing that was allocated is on the heap, but the pointer to the allocated region is on the stack. And there may be other bookkeeping needed to call a function, like the return address, so that when the function that is called executes its last statement or a return statement, we know what value should be stuffed back into the program counter in order to transfer control back to the caller. So that's just generally called the stack frame, and it's what's used to keep a hold of all the information needed in order to create an execution context for the function that's being called. So if that's what a routine is, a subroutine, what is a coroutine? So a coroutine, if you look it up on Wikipedia, now coroutines have been around since the 1950s, so they've been around for a very long time, even if they are newly added to C++, relatively speaking, 2 standards ago, right? Not C++23, but C++20. And the idea of a coroutine is a function whose execution you can pause. Now, if you know how preemptive multitasking works on most modern CPUs, the exception might be something like a microcontroller. Preemptive multitasking is implemented by the operating system typically. Might have support from the CPU hardware, but typically it's implemented by the operating system. Functions are paused all the time. You have a time slice that the operating system gives your process, and when your time slice is exhausted, then the operating system interrupts your executing code, saving an execution state somewhere, and then transferring control of the CPU to somebody else to let them run for a while. That's preemptive multitasking. Coroutines are the building block for cooperative multitasking. This in the early days of personal computers, in order to get multitasking implemented, they used cooperative multitasking. This was most widely done on the early Mac OS before it changed to OS X. OS X is preemptive multitasking, but Mac Classic OS is cooperative multitasking. The idea of a coroutine is that the function itself, at certain points within the body of the function, declares that there are certain suspension points within the code, and at those suspension points, execution may be suspended. It's not guaranteed to suspend. Like, for instance, you may be in a situation where you wanted to wait on something to happen, but at the point where you were going to wait on it, it already happened. So there was no point in waiting and suspending yourself. You just continue on with the thing you were waiting for because it was already available. But within a coroutine, there are suspension points, and in those suspension points, if the coroutine is suspended, control is transferred back to the caller, and then the coroutine can be resumed after the suspension point at a later time. Now, coroutines kind of, get mixed in the jumble of concurrent things you can do. So in the standard library, we have stood async for asynchronous programming, invoke an operation asynchronously. We have threads for multi-threaded programming, where you have multiple concurrent threads of execution. Those multiple threads are scheduled onto cores in a multi-core CPU, and those are truly executing in parallel. With a coroutine, the idea is there may be some operation that you initiate, but you won't get the answer for some time. The obvious use case being network I/O. We saw this with Boost as I/O when we looked at timers and serial ports and sockets and HTTP traffic and WebSocket traffic. Communicating outside the CPU takes many orders of magnitude more CPU cycles than computing a value into a register or computing a value locally into memory. So those are relatively slow operations, and what you'd like to do is initiate that operation and then just wake up later when the operation has completed, or when, if it was a request for reading data, when the data is available, if it was a request for writing data, when the writing the data is complete, and so on. So just like Boost ASIO, where you can schedule a bunch of asynchronous operations to happen, and then there's a scheduler, an event loop that you pump. Here, there's no explicit event loop, but there's these functions where you can initiate operations and wait on them to give you an answer, and you can then schedule the coroutine, as you see fit. So basically, you're writing your own event pump, your own scheduler to decide how these coroutines execute. So in C++20, the coroutines are stackless in the sense that all the execution context needed for the coroutine is allocated on the heap. It's allocated by the compiler. There are mechanisms available to you that you can control how that allocation takes place, and in many cases the allocation can be omitted, optimized away by the compiler. The three new keywords in C++20, co_await, co_yield, or co_return, if any of those keywords are present in the body of a function, then that function is a coroutine. So there's no special attribute or special keyword that introduces a coroutine in the declaration of the function. There's just the presence of these keywords inside the body of the function is what designates the function as a coroutine. And that can be inside a lambda, can be inside a member function, can be inside a free function. Obviously, with lambdas, you have to consider the lifetime of the lambda, because the lambda produces a value, right? So you have to make sure that the lambda survives as long as you are executing this coroutine by resuming it. And there's really three types that interact with each other to implement a coroutine. There's a wrapper type, and this, when you write a coroutine function, the return type of the function specifies the type of the wrapper. Now the wrapper, when you call a coroutine function for the first time, really what you're doing is executing a factory function to create the wrapper. The wrapper is going to be the type that exposes some sort of API to clients of the coroutine. It's going to be how you are going to communicate things in and out. This question in the chat that they're not hearing audio. We're just going to keep going because we're recording, so if things don't work, we can always get the recording on YouTube. So that's the wrapper type. It exposes the API to clients of the coroutine. Now, a nested type inside the wrapper is called this promise underscore type. And that's not, it is conceptually a promise, but it is not a stood promise from the async, stood async land. It is literally called promise underscore type, has to be that identifier inside the wrapper. And this is the thing that you use to customize the behavior of the coroutine in terms of suspending and resuming and so on. We're going to look at that in more detail when we get into the code example. There also there's a concept. It's not a C++20 concept, but it's conceptually a thing called an awaitable. And the awaitable is basically how you're going to marshal data between the coroutine and the promise type. We'll see what this means in a few minutes. But so the thing to think of is there's this wrapper. It has a nested promise type, and then there are awaitables that interact with the promise type and the wrapper in terms of getting things done. Okay, so what are these new keywords? What do they look like? So a co-return, it can take an optional expression because some functions return a value, some functions don't. Some functions, have a return type void and they don't return a value. So the expression argument to co-return is optional. And this exits the coroutine with a returned value if the function returns a value. And typical use case here is to early exit from the coroutine or returning a final value. In the case, you can think in the case of like a generator coroutine, it might have a loop where it's pumping out values, and then after the loop exits, it returns one final value. Or maybe you've got some situations that allow you to determine that you're not going to be able to produce any values, and you co-return as an early exit. And this makes it so that the simplest coroutine that you can write is just a function that simply calls co-return with no value. So this coroutine, it doesn't do anything. It has a wrapper type that is the return type of the coroutine function. And it is a coroutine by virtue of the fact that one of the statements inside the body of the function calls co-return. There's co-yield, where this allows us to compute some value and communicate it from the coroutine to the client via the wrapper. And this suspends execution of the coroutine as the value is communicated out. We're going to see how this is connected to the promise type and the wrapper when we look at the example that we're going to the code example that we're going to look at later. and the typical use of co-yield is if you've got a generator. So the idea of a generator is you have this function that you call, and it keeps producing values until it doesn't have any more values. Now, if it's generating an infinite sequence, you could call it, as many times as you like and always get another value out, and it'll always say, I have another value waiting for you if you ask it. Now, coroutines being suspendable entities, this lets you write lazy functions that perhaps computing the values is quite expensive, so you don't want to compute them up front. And if you have an infinite sequence, we obviously can't store all the elements of the generated elements. We can't store them all in a vector and then return an iterator to the vector, because the vector would have to be infinite size. So the idea here is, with lazy execution, we can call this generator as we need values, and if we never call the generator, if the values were expensive to compute, we never spent any time computing values that weren't needed. Co-await on an expression, actually I think it might be a mistake in my slides here. I think the expression is required. It can't be optional. The expression is is an awaitable, and this is basically a way to compose coroutines together. So in a sense, so you can, for instance, if we were doing some kind of network operation, getting an HTTP request. Well, the first thing we're going to do is take the host name and try to resolve that to an IP address. Well, that's an asynchronous operation. We could have a coroutine that did that. Then the next thing that we're going to do is take that IP address and try to connect to it. Well, that's an asynchronous operation. We're going to be connecting a socket to a remote IP address. And then after we've connected the socket, we are going to write our HTTP request over the socket to communicate a request to the server. That may be an operation that it's going to take us multiple asynchronous write operations in order to do that. Then we have to read back over the socket the response from the server. That may require multiple asynchronous read operations. So you can see in that sequence of events, there's a whole bunch of asynchronous calls that we're going to do. And we saw when we looked at ASIO that we kind of wired things up with callbacks and an execution context that was maintaining the intermediate state, so that we could compose necessary structures representing an HTTP request and an HTTP response. So in a coroutine style of programming, we would just have a linear function, this coroutine, and it would just be co-awaiting on each of these steps as we got progress through the sequence of operations that we needed to do asynchronously until we got the final answer. Now, there's no guarantee that you will suspend when you co-await on an awaitable, because the awaitable may represent something that's already happened. For instance, suppose you're waiting on a timer and the timer already timed out. So if the thing you were going to wait on was already available, it may just return the answer to you right away and continue execution at the next statement. Co-await can return a value. You can await on a thing to get a value back, but you can also just await on a thing to see if it, to get notified when it happened, when it was completed. So an awaitable, it's really just a class with three methods. There's await ready, await suspend, and await resume. So await ready returns a bool saying whether or not this thing is suspendable, whether it is ready to wait. Await suspend is what happens when another coroutine is being suspended, and the thing that's being suspended is the argument to await suspend. And then await resume is the code that is executed when the awaitable is resumed. And most of the time, if you're dealing with low-level coroutines, as we're talking about today, you won't need to write your own awaitable. Most of the time, you just use two trivial awaitables that are provided in the coroutine header: suspend never and suspend always. And suspend never indicates that the await expression never suspends, so you call co-await on something that was suspend never, and it just immediately returns. You call co-await on suspend always, and it always suspends. And we'll see when we look at this promise type that's associated with the wrapper that we're going to end up using stood suspend always and stood suspend never as the return types of customization points that we're going to implement in the promise. Okay, so how does this all really work? Well, what the compiler does is it transforms your coroutine by decorating it with function calls. There's going to be some code that's going to allocate this chunk of execution context on its execution state on the heap. It's going to take the parameters that are passed into the coroutine function and store copies of them into that execution state. It's going to set up space for local variables and attach them to locations of memory inside that execution state that was allocated on the heap. And there's a standard type called a coroutine handle, and the execution context is associated with the handle. Now, for places where you have maybe some kind of C-style API where you need to specify a callback function and an associated void star context pointer, there's a way to marshal a raw pointer, a void star, back and forth between a coroutine handle. So from a void star, you can get the associated coroutine handle, and from a coroutine handle, you can get the associated void star. So if you have some kind of C-style API that you have to glue your coroutine into, there's ways to do that, to glue those things in. It's going to take the coroutine function body, and it's going to insert various function calls in there that are going to implement the suspend points, and those function calls are essentially going to be calls to method on the promise type. So that's how you can customize the execution of the coroutine, is because basically the code that you supply is going to be glued in there. They're typically all implemented as inline functions, or inline methods rather, on the promise type. So the compiler is going to be able to inline your customization directly, so it's not going to result in additional, indirect function call through a virtual table or anything like that. And the co-return, co-yield, and co-await expressions, those are also going to be replaced with function calls relating to the promise type. So everything that the coroutine does in terms of its unusual behavior, which is its ability to be suspended and resumed, that is all connected to the promise type by the compiler. And the three types are connected because the promise type, it has to be named promise underscore type inside the type that is the return type of the coroutine. So if the in this case, the return type of the coroutine is some class called wrapper, there must be a named type called promise underscore type nested in the wrapper to define the associated promise for this coroutine. Now, the promise type can be named as like a type alias or a actual nested type that's defined inside the wrapper. It's not required to be defined as a nested type. It just has to be accessible by referencing that name. The coroutine handle, as I mentioned, that's convertible back and forth from a raw address, is parameterized by the promise type, and there's a way to obtain the promise from a pointer to the promise instance from the coroutine handle. We'll see what that looks like when we get to the example code. And the final piece that connects it together, so we can get to the promise type class, that its type, by looking inside the wrapper. We can get to an instance of the promise from the coroutine handle. So a coroutine handle is associated one-to-one with an instance of the promise type. And then the promise type constructs the instance of the wrapper that is returned by the coroutine when we initialize everything. So from the point of view of the caller, the coroutine function, it looks like a factory function that returns this wrapper. And the mechanism that does that is controlled through a method on the promise type. It's a little bit goofy. It's kind of weird that you just didn't, you write your coroutine function body and it has a return type wrapper, but nowhere in there is a thing that says, return wrapper, initializing expression. And that's because the coroutine, it's declared as having a return type of wrapper, but if it has a return value, that value must be returned via co-return, and that's a different type, a different expression. So this is a little bit confusing to talk about. I think it'll become clearer when we look at code. So that's what the compiler does. It's generating this. It's allocating this chunk of memory on the heap for the execution context. It's transforming the body of your coroutine to change these keywords into function calls, and it's connecting things up from these different types. And what you do as a developer is you get to choose the client API of the coroutine by writing methods on the wrapper. So typically the client of the wrapper does not directly interact with this coroutine handle or with the promise type directly. That's all just underlying machinery of how the coroutine is implemented. So it's kind of hidden away, and you have a more convenient client API on the wrapper type. And you customize the behavior of the coroutine by writing methods on the promise type that's named inside the wrapper. And there's a few methods that you must write, and then there's some methods that are optional. We'll look at, in my code example, I'm obviously implementing the ones that I must. And the compiler is going to be good enough to tell you, if there's a required method that you didn't write, it's going to tell you, I tried to access this method and it doesn't exist on the promise type. And the developer gets to choose the suspension points inside the coroutine when they use co-yield, co-await, and co-return. There's additional opportunities for choosing suspension by the methods on the promise type, which we'll see when we look at the code example. And these interface types associated with coroutines, they're not interfaces in the sense of like the promise type. It's not a pure virtual interface. It's not a concept template argument to the coroutine. It is kind of like, you can kind of think of the promise type and the awaitable as defining a contract. And so there's requirements on the names of methods and the types of the arguments that they take and the types of the arguments the return type. So you can think of it as a set of requirements on these classes, and they're abstract in that sense that they have a certain specified semantics, and you have to implement them. But they're not virtual interfaces. They're not pure virtual abstract interfaces. So there's no indirect function calls, and because everything is typically inline, the compiler has the opportunity to, squish away implementations to give you the most efficient implementation of the coroutine that follows the policies that you've chosen by the customization points through your promise type and your awaitable. All right, so why is this so complicated? Well, it's because this is intended to be a low-level coroutine API to serve a broad range of use cases. And there's a little bit of glue support in the standard library, this coroutine handle, and the it's always suspend and always or what did I call it? What is it called? Suspend never and suspend always. I just want to make sure I was saying it correctly. So there's a little bit of support in the standard library, but that's about it. There's no coroutine algorithms supplied yet, at least not in C++20. I'm not 100% certain if any made it into C++23. I think maybe there's a generator API that made it into 23. And for simple coroutines, once you get the hang of it, it's not so bad. But it is anticipated that this low-level API will be used by higher-level libraries to express cooperative multitasking at a higher level. For instance, you might say, I've got a bunch of asynchronous things in process, and I just need to know when the first one of them completes and gets a value. Right? So that's a bunch of coroutines are running, and the first one to say, hey, I got an answer, that's the one I want the answer from, and the rest of them can be canceled. And those higher level operations, it's intended that those will come from libraries, whether it's a standard library or a user-written library. Next month, we're going to look at Boost Cobalt, which is a relatively new library. It's only been in 2 Boost releases so far. And it operates at this higher level. So in order to talk about this library, we kind of first have to understand coroutines and how to do it manually ourselves before we look at an easier way to do it. So we're going to, it's like I always say with code generators, you should know how to write that code manually before you start using a generator, because otherwise it'll just be too much like magic. You won't know when is the appropriate time to change that generated code with hand edits, or when is the time to change the generator so you get different variations and whatnot. So that's what we're going to look at today. Now, Andreas Weiss, he's put together a nice coroutine cheat sheet. This is out on GitHub, and I've just included a little bit of it here. So again, we're gonna the return type is a class that we write that represents the client API for our coroutine. Now, he's got little /stood coroutine traits there. So the coroutine traits, we're not going to go into the details of it, but the point of coroutine traits is to allow you to adapt an existing type for use as the return type from a coroutine without changing that existing type. So for instance, if you wanted to adapt a return type for an existing library, which you don't have the source code, you just have header declarations, you could make that return type usable as a coroutine through coroutine traits. And so inside the return type, the return type is our wrapper. So inside there's this nested promise type. You can have an optional constructor for that promise. There's the method get_return_object, and you notice that the return type of this method is the wrapper type. So that's this getReturn object is the thing that actually constructs the wrapper from the coroutine handle. There's initial suspend and final suspend, and you notice he's written stood suspend always as the return types of those. This is how you customize what happens when the coroutine is first invoked. Does it suspend immediately before you execute any code inside the function body of the coroutine? And when the coroutine exits via just falling off the end like a normal function or via co-return, does it suspend one more time at the end, or does it just immediately exit and delete its compiler allocated heap memory that represents its execution context? So for both of those customization points, he's written the return type as stood suspend always, so that when we start a coroutine, it always suspends at the very beginning. And when the coroutine finishes execution, it always suspends one more time at the end. There's these two functions, two member functions, return value and return void, that handle the results of co-return. So if co-return did not have an expression as an argument to the co-return statement, then it invokes return void. If the co-return returns a value, then this return value parameterized by the type of the expression that was given to co-return is invoked. A function can either, a coroutine can return either nothing, in which case you implement return void, or it returns a value, in which case you implement return value. It is an error to implement both. So that's why he's got a slash there between those two methods. Unhandled exception, we haven't talked about exceptions at all. What happens if an exception is thrown inside your coroutine while it's running? Well, what happens is the unhandled exception method on your promise is what's invoked. It turns out part of the decoration of your coroutine function body that the compiler does is it wraps the whole thing in a try-catch. And in the catch, if an exception was caught, it will invoke the unhandled exception member on your promise. And one of the things that is typically done is to implement the promise in such a way that it holds a variant of either the value that this coroutine is going to return or an exception pointer, and when you go to get the value out of the promise, it says, oh, actually what happened when I executed the coroutine, it threw an exception. I've kept the exception pointer stashed off, and you've asked me for the value, but what happened is an exception, so I'm going to take that exception pointer and kind of rehydrate it into an exception and throw that. So you attempt to get the value, and then an exception is thrown, and it unwinds your code normally, as you would expect. In my example, I'm just taking the cheat sheet, easy way out, and I'm just calling stood terminate if we get an exception. Here's the interface of the awaitable. Now, he's just written struct awaitable. This is not, there's no actual class named awaitable in the standard library. Stood suspend always is an implementation of this interface. And for suspend always, await ready always returns true, I believe. We'll double check that in a second when we look at CPP reference. But an awaitable implements these three methods. It can have other methods, but these three methods are required. So the suspend gets access to the coroutine handle of the thing that is being suspended, and await resume and await ready are how you control the suspending behavior of the awaitable. So here's kind of like a kind of a call diagram that shows you how these things are related. The caller of the coroutine gets access to the return type. That's going to be the client API. And it's constructed by getReturnObject from the promise, constructs the return type. The return type is associated with the coroutine handle. In his case, he's storing it in a .handle member variable of this return type class. We're going to see what this looks like in real code in a second. I think it might be a little more clear. And the handle, you can get to the handle from a promise by calling from promise on the handle. This is a static method on the handle. If you can, from the handle, you can get back to the promise by calling the .promise member function. In the coroutine, when co-yield is called, that ends up resulting in calling this function yield value on the promise. And if the coroutine does co-await, it's waiting on an awaitable, and that awaitable interacts with the coroutine handle through await suspend, or it comes back to the coroutine with await resume. So let's take a look at some code here. First, we'll take a quick look over at CPP reference. So the standard that describes these keywords, it's a really tough read, and CPP reference is better, but still a lot of information is shown here, and a couple simple examples are given, but it's difficult to read through this to figure out how to get things going. I've got a little repo here where I took our SIMD-JSON comic book database that we talked about a little while back, and I've simply, this was a database where it's an in-memory database reconstituted from a bunch of JSON on disk, and then I had a little program that would do a query against this database and print out the results. What I've done for the coroutine version is I've changed it so that the query, the thing that returns the query results, is a coroutine. So every time I ask the coroutine, do you have another match? And it says yes, and then I ask it for the match, and I keep doing that, and the client of the coroutine and the coroutine are ping-ponging back and forth in terms of what is being executed as the coroutine loops over the database to find matches and returns them one by one with a co-yield. So let's take a look at that code. Let me make this font bigger and bring this over here so you can see that. Okay, so let me close all these things. Close all tabs. So here is my header file declaring my coroutine API. So I have this little pure virtual abstract database here. I'm gonna have a SIMD DOM element representing the issues. So in this database, there's two JSON files. There's a JSON file representing issues. So these are different comics that are, issue number 1 of Amazing Spider-Man, for instance. And then within each issue, there's one or more comic stories that are called sequences. So the sequences have a key that indexes back into the array of issues. So I just have two methods on my little database here that allow me to get the issues and the sequences. It's coming back as a DOM element, but it's really just an array of objects. And I have a little factory function that creates this abstract database using a directory on disk that contains the two JSON files. So as we did before, we're going to query this database for credits. So a credit is either credited with writing the script, or credited with doing the pencil art, or credited with doing the ink art on top of the pencils, or credited with doing the coloring on top of the final inked art, or credited with doing the lettering. So all the letters in a comic, typically they're not typeset, they're typically written out by hand by someone. So all of these different types of fields within a sequence have an associated name with it, possibly, if the name is known. And that's what we're going to do, is we're going to query this database for a particular field with a name, and we're going to get back from our coroutine, one at a time, we're going to get a sequence match. So there will be a JSON object, so a bag of name value pairs that represents the issue, and a JSON object that represents the sequence within that issue that matched our query criteria. So before we look at the promise in detail, let's look at our match generator. This is our client type. So here is our coroutine, the declaration of our coroutine. This is our wrapper type, match generator. And I'm passing arguments into the coroutine. The compiler will make space for these arguments within the execution context that's allocated for the coroutine and associated with its handle. So this is a smart pointer to that abstract database, an enum that represents the field that we are querying on, and a stood string view that represents the value to be matched against the field that's in the JSON. Okay, so our client API, from the point of view of the caller, we'll look at this destructor in a second. So we have a constructor that's private. So the only way we can get one of these match generators is by calling this coroutine that's going to act like a factory function to give us this wrapper, an instance of this wrapper type. The copy constructor and the copy assignment are both deleted. Just for simplicity, you can get more complicated with things. This resume method, it's going to return true if this coroutine has more data available. So we have this coroutine handle. I've got a type def for it here. It's a stood coroutine underscore handle of our promise type. Our promise type is just a using alias for this nested struct. We'll look at the struct in a second. And to know whether or not we can resume, well, we can't resume if we don't have a handle, or if the handle says that the coroutine is done. For instance, we did a co-return, so there's no more code to execute. We're just suspended at the end of the execution of the coroutine, but we haven't cleaned up yet. So in those two cases, we can't resume. Otherwise, we're going to tell the handle to resume, and that's how we communicate to the coroutine that if it's ready to continue execution from its last suspended execution point. Then we're going to ask the handle if it's done, and if it's not done, then it means there's more values, more work that we can do in our coroutine. Now, so from the point of view of the client, what this looks like, we just got a bunch of code to print out things, and we're going to look at this loop here. So here we're creating our coroutine by calling that factory function, and as long as the coroutine can be resumed, it has more stuff waiting for us. We're going to resume it, and then we're going to get the match out, and then we're going to do that again. So we'll just keep iterating. As every time co-resume returns true, it means there's a match waiting for us. We're going to keep getting the match as long as the resume returns true. So over here, this get match, it's going to, remember I said you could get to the instance of the promise associated with the coroutine by calling the promise method on its handle. So we're going to get at that promise, and inside there is a nested data member called m_data that holds the current match. We're going to grab that out of the promise, then we're going to reset the promise to an empty match, and that way you have to ping pong back and forth between resume and get match to get useful data. We're going to then return that match. So this is the client. This is the whole client API. There's a resume and a get match. Now the glue that is used by the compiler to connect all this stuff together is really inside the promise. So this get return object, remember I said there was this static from promise method on the handle that we could use to obtain the handle associated with the promise, if we look at that, if we drill into that into the standard library, it takes the promise by reference. So that's why we pass star this. We pass the promise by reference into the from promise. This is a static method. It gives us the coroutine handle, and we use that to initialize our wrapper type. The constructor for the wrapper is just taking that handle and stashing it in a member variable so we can access it. We're accessing it down here in our resume method, and we're accessing it here in our client API for getting the match. So that's get return object. Really straightforward. This is pretty much always going to be what you do when you implement get return object. That's not to say you can't do other things. You can do whatever you want. But this boilerplate is typically what you will do. Our initial suspend is going to be stood suspend always. So that means as soon as we invoke this coroutine, remember this get return object will be invoked to return the wrapper type, and then at that point the coroutine has an execution context and it could start running. This initial suspend determines whether or not it does start running. Here we're saying suspend always, so as soon as the coroutine has an execution context, it suspends. Similarly, for the final suspend, we're going to use suspend always. So when the coroutine starts to leave the body of the coroutine, either with co-return or just falling off the end of the function body, it will also suspend at that time. Our yield value, so when we call co-yield with something that is convertible to a const reference to a sequence match, this yield value overload will be called. You can co-yield different types at different points inside your coroutine body, so they're not all required to co-yield the same type. So I could co-yield an int in one place and co-yield a string in another place, and that's fine as long as you have an appropriate overload of yield value that accepts an argument that your yielded value can be converted to. In my case, it's exactly a sequence match object, as we'll see when we look at the body of the coroutine. And all of the promise is going to do at that point, when you co-yield that value, it's going to be, great, I'm going to stuff that in my data member, and now I've got it. And then I'm going to return a default constructed stood suspend always instance, right? There's a return type. This is a class, stood suspend always, right? It returns false for await ready. I think I had that backwards when I described it before. The suspend never returns true, and the suspend always returns false. And the other two methods don't do anything. They're empty implementations. So we're always going to suspend after a co-yield, is what that means. When I say co-yield and produce a value, it's going to be squirreled away in the data member of this promise class, struct really, and then we're going to suspend. If I do a co-return from my function, in my case, my co-return cannot have a value. I can only do co-return with no argument, because if I implemented return void, and you have to either implement return void or implement return value. I'm implementing return void, which means co-return can be used, but it must not specify value. A good compiler will flag it as an error, otherwise it's undefined behavior. But I don't need to do anything, so it's just an empty function. And my final suspend, I don't need to do any extra work, but I want to indicate that it should always suspend when we exit by any path from the coroutine. My exception handling behavior is I'm just going to call stood terminate and die. I do have exception exceptions that can be thrown from some of the code that I'm calling. So if I wanted to do something better, I would, like I said, stash away the exception pointer into a data member into a data member in the promise, and then when I call get match down here, I would check to see if an exception was thrown, and I would rethrow the exception from get match. That would be better error handling. Right now, I'm just doing something straightforward. I have this data member. It is mutable. Actually, I don't think it technically needs to be mutable, but I've implemented as mutable. So that's everything that's going on in the wrapper. So now let's take a look at what the coroutine, the actual body, looks like. So this database, it's coming in as a smart pointer. Well, what if they passed me, an empty smart pointer? So I'm going to check for that. And if that happens, well, there's nothing for me to search through, so I'm just going to co-return immediately. So this coroutine is all over if you give me an empty smart pointer to the database. I'm going to have a little map here that I'm going to use as a cache, so I'm not scanning the many gigabytes of JSON that represent all the issues that I've scraped up from disk. There's going to be a map from the issue ID to the JSON object that represents the bag of name value pairs that constitutes an issue. I got this thing in by enum from my query, which credit field I'm going to query against. But in the JSON representation, all the names of all the fields are strings. So I'm going to take that enum, convert it to the appropriate string, and that's now my field name. It turns out my toString, it returns a string view because I'm just returning string literals for the different things. So it doesn't need to actually be dynamically allocated, so it can be a string view, and the lifetime will be just fine because the string view will be pointing to a literal string, not some kind of dynamically computed string whose lifetime might have expired. Here was our call into the database. So we're going to get the JSON element that represents the sequences file. So it is a SIMD JSON result containing a SIMD DOM element. From there, we will get the array associated with that element. If I wanted to do more error checking here, I would validate that this thing is indeed returning an array. I'm just assuming that it is. And if it's not an array, SIMD JSON will throw an exception, and we'll go back to the method unhandled exception on our promise type, and we'll just call std terminate. So again, simple error handling here, not elaborate error handling. And again, I'm going to do some checking. If the elements in this array, so remember JSON, an array can contain anything: numbers, strings, null, other arrays, objects. I'm expecting this to be an array of objects. So if the thing I got out of the array is not an object, I'm going to throw an error. This is pretty much copied and pasted and modified slightly from my version that did all the query in memory and returned it all as a vector of results, as opposed to giving the results back to the client one at a time like we're doing here with a coroutine. So we're just going to drill through this JSON to get at the field whose name matches the field name, and then we're going to look at the value associated with that field and look for the credit name that we're searching for. So this credit name is someone's name or a substring. We're just going to check that credit value, and if the name was a substring in there somewhere, then the object here is the sequence associated with the match, and here we're going to get at the the object associated with the sequence, so we can look up the issue field in the sequence to go and find that in our little cache. This issue field isn't guaranteed to be a number, so I'm calling S2I on that to get a number out. I'm looking that up in my little cache of issue number, or issue ID rather, to a JSON object that represents the name value pairs associated with the issue. If we got that, if we looked it up and it wasn't found, then we need to go find it out of the database. Once we found the issue and we know what sequence we're in, so an issue is a collection of one or more sequences, and the match that we're going to yield back from our coroutine is this this little struct here. It's just, two JSON objects, one representing the issue name value pairs and one representing the sequence name value pairs. We're going to co-yield that back. Now, what happens if we don't get any matches? So we come in, we have a valid database, so we didn't co-return here. We searched through all this stuff. We didn't find any matches, so we're going to fall out the end, and it's as if we did a co-return right at the end here, but it's just an implicit co-return. We fall off the end, and execution is suspended. The rest of the code in this file is just kind of little helper functions. Here's my my little JSON database. It gets the directory, and it's going to go and scrape up the files on disk and turn them into SIMD JSON results that we're going to use to return back so they can be queried in the coroutine. And if we look at the main function, which we already looked at, so as long as we got results left, we're going to go and print one. And if we go over here, I've got this set execution arguments. Here's the path to my local directory on disk that has those two JSON files in it. The -s argument is what I use to say query the script field, and then here's the string that I'm going to query against all the sequences. And if we run this, we will see that it takes a little bit of time. This is a release build, so it doesn't take too much time. It takes a little bit of time to read the couple gigabytes of JSON that represent the issues and sequences, and then it's printing them all out. So it's working. Let's stop this and take a little bit deeper look inside the coroutine from some test cases. So all this stuff, there's like a lot of moving parts, right? You got to write this promise class, you got to write this wrapper class, and you got to figure out what awaitables you're going to be using, and how are you going to do? Are you going to do co-yield? Are you going to do co-return? What are you going to do? So I've written a little set of G-test unit tests here. I've got some, simplified, just a few records of these JSON text that represents the issues and represents the sequences. I'm using a raw string literal type, so I don't have to worry about escaping all these backslashes or whatever other weirdness might be inside these strings. I can just kind of copy and paste it in there. And I've got a mock database, so I can mock out the methods on my abstract database. I'm just going to have a little helper struct here that represents parse JSON. I'm going to take the JSON in as a string. I'm not going to read it off disk. I'm going to invoke my little SIMD JSON parser to parse that string into a document, and I will use that in my tests. And here's kind of, an interesting test. I said before that, we don't want to do anything if we've got a null pointer database. So if we put a breakpoint here and say debug this test case, I'm using the gtest support in ReSharper for C++. It understands Google test. Oops, I should do this in a debug mode. That's why I didn't stop on my breakpoint. We can bring this over here. You can see that my tests are actually passing. This is their little unit test explorer test runner. Okay, so I can select this guy and I can say debug that test. And now I've switched back to a debug build, so we should hit this breakpoint. Now, we've already constructed our match generator. Let's bring locals over here. Bring autos down here. So here's my coroutine, right? It's got this handle data member that has the associated promise, and the promise has the data member inside of it. And that data member is a pair of DOM objects that represent the issue and the sequence from the parsed JSON. And right now those are empty. So this data is empty. And now we'll leave that alone in terms of size. Okay, so we'll step inside here. So now we're going into the client API on our wrapper type. Our wrapper type is match generator. We implemented a method called resume. So we're going to step into that resume, and we have a handle. So over here, this handle is valid, and we haven't executed the coroutine at all yet, so it's not done. So we're going to tell the handle, go resume the coroutine. I'm going to go over here to my coroutine implementation. I've got a breakpoint there. So when we come back here and I say resume on the handle, it's going to invoke the coroutine from its last suspend point. Now, since in our promise type we said it always suspends at the beginning of the coroutine, so we haven't executed any code at all yet in here. This is our first time in. We're resuming from our very first suspension. And we're checking that database, and then we're calling coreturn. And if I stepped into coreturn, and you see coreturn, there was some kind of compiler-generated shim, but it ultimately called return void on the instance of our promise. Let me step into this function. So now that the this pointer on the promise has been hydrated from the stack, and if we needed to do something special when our coroutine returned void, we could do it here, but we don't need to do anything, so it's empty. I come back out, and then I step again, and then we're leaving the bottom of the coroutine. And the reason it jumps down to the bottom instead of just immediately executing is because the compiler has inserted that final suspend point at the end of the coroutine. So if I step in again, we see we're inside the final suspend method of my promise type, and we're going to say suspend always. So if I step in again, now we're in constructing that suspend always. I step in once more, and now we're in coroutine handle from address. So somebody is getting the coroutine handle for my coroutine from the address of the execution context. Now that I've stepped into the function, you can see it's some reasonable value. Step out of that, step in one more time. Now we're constructing the coroutine handle, an empty coroutine handle, and now we're inside await suspend. So this is the await suspend implementation for suspend always. And if I step in one more time, we're out of that. It was empty braces, and now we're inside the resume of, let's see, we're in the final bit of the resume of this handle. So if we step out from that, so now that's what happened when we called handle resume. Our coroutine was initially suspended at the start of the coroutine. We executed some code, got to a suspension point where we did co-return. That suspended us at the end of the coroutine, and our customization points were poked because we're in a debug build, so they didn't get compiled away. And one too far. And now we're going to ask the handle if it's done and return not done. So when we come out of my client resume, the return value was false. So that means there's no more values, right? We can't resume this thing to get any more useful data because it's already done a co-return. So resumable is false, and our test passes because we expected it to be false. Now, let's look at a more interesting, kind of not edge case scenario, where we will look at what happens when the coroutine is invoked multiple times. So here, let's get the cursor down here. Creating my mock database. I'm parsing JSON from the issue literal string that I had up at the top of the file and the sequences literal string at the top of the file. I'm expecting that the database will get called once with get sequences, and it's going to return the sequences JSON document, and it's going to call, I'm expecting that the database will have get issues called, and it will return once the issues document. I'm going to construct my coroutine. I'm going to call resume on it. Then I'm going to ask for a match. And then I'm going to call resume a second time. And I expect that it should have reported true when I asked it to resume the first time, meaning there was a match. And I'm expecting also that when I asked it for a second match, that was true. And then I'm just going to poke briefly at the match that we got out from calling getMatch to validate that we were doing a script query with this script name. So that means when I ask the sequence for the value of the script key as a string, that value better contain my query text as a substring. So let's try this in the debugger and see what this looks like. If I go over here, say debug. Okay, so we've constructed our coroutine, wrapper type, the match generator. We're suspended at the beginning of the coroutine. We will call resume. I'm going to step in here. I'm going to step into handle resume. That's going to call this built-in. Now we're inside the coroutine. We do have a database. We initialize our little cache of IDs to JSON objects that represent issues. The reason we're doing that little cache is because as we obtain results from the sequences list, it's going to be the case that more than one sequence is going to match the queried credit inside the same issue. So remember I said an issue has one or more sequences, and it's likely that multiple sequences are going to match on the same issue, so we don't want to be scanning that big JSON array looking for the issue object every time we get a match on the sequence. And these local variables, they are part of the execution state that was allocated on the heap for this coroutine. And actually all these local variables that are in here, their storage, their addresses, is all within that heap allocated chunk of memory. Remember, we're not using, these are stackless coroutines, so all the local variables are not allocated on the stack. They're allocated in that chunk of heap memory allocated by the compiler. So we're going to walk over each of the records in the sequence array, and we'll just put interesting part is when we get down here. So we'll do Control F10 to continue execution to the cursor location. We didn't find the issue in our little cache, so we will go get that. There's no coroutine business in here. This is just a plain ordinary function. We get that, store it in our little cache, and then we will co-yield that sequence match. So if we start stepping in, here we're calling yield value that has our two JSON objects that represent the sequence and issue for the match. We will stuff that in the data member, return suspend always. If we keep stepping in, now we're constructing that suspend always, or the construct always was suspended. We are calling the await ready method. We will keep stepping in. Now we're calling coroutine handle from address. Stepping in more. Now we're getting an empty coroutine handle, or the coroutine handle for this promise. Let's see, the underscore pointer has a value, so that's the coroutine handle for this promise. Step in again. Now we're calling the await suspend, which does nothing on stood suspend always. Step in again. Now we're calling this built-in co-row resume. This is the implementation of coroutine handle resume. You step out of that. We've just finished executing the resume of the coroutine, and when we return from that function, it returned true, saying there's still more to come. So we can get the match out. Let's step in to see what it looks like to access the match. We're going to get the promise object instance associated with this handle. So when we step into that, this thing, it simply does some casting magic around to get a reference to the corresponding promise. How that exactly is implemented is up to the implementer of the standard library and the compiler, but it's an inline function that's just doing some casting. So when we do an optimized build, it's going to basically amount to moving an address into a register. We're going to get the mdata out of our promise. We're going to null out the mdata that's in the promise, return that match, and then the second value also returned true. So when you're implementing coroutines, my recommendation is to do a bunch of unit tests like I've done here, so that for the different scenarios that you care about, you're confident that your coroutine is doing what you expect. So in my case, I say it shouldn't be resumable from only one match. So in this case, I've asked if there's the first match, and it said yes, expect true. I get the match, and then I ask if there's a second value, and that should be false. So here's a case where we are expecting only one match. Why are we expecting only one match? Because I've handcrafted the JSON for this mocked up database, so I know exactly what it should be doing. Right? It's not reading gigabytes. It's got 2 records for the issues array, and it's got like 4, 6, 7 maybe records for the sequences array. So I've looked at my input data and said, oh, well, this name appears only once as a letters credit. If we search through my little text strings here, you can see it appears only once in the sequences array as a text, as a letters credit. So when I'm searching down here, I'm going to search for letters credit, and I know that this name matches exactly once based on my test data. I can test my coroutine and validate that everything works as expected. Now, inside our generator here, I've implemented the bare minimum needed for my promise type. There are other methods that you can implement to further customize the behavior. You can customize memory allocation. There's also additional mechanisms that you can use to associate awaitable types with another type. So you can, say, co-await and provide a value of some type, and then there's a way to associate a different the awaitable with that type. So that allows you to use co-await on data types and use them as awaitables even when they come from third-party libraries and they weren't written as awaitables. So there's a lot of customization points in this mechanism, the coroutine mechanism, that you can supply. But this is pretty low-level stuff, right? I mean, we got it working, and we have confidence that things aren't going crazy because we wrote some tests. And actually, I did this test-driven, so I started with something that just did like the database check, and as I said, some of this code is throwing exceptions, and in my simplistic coroutine interface, I'm just calling std terminate, and that manifests itself in a gtest run as, the test executable crashed and none of the remaining test cases were executed. So, not the best error handling, but, you can work your way through it. There's more sophisticated error handling that should, strictly speaking, be done here because this code that is being called by the coroutine is throwing exceptions. So this is not the best way to handle exceptions. But this is the minimum that you need to implement in your promise. There's more methods that can be implemented on the promise to customize more behavior. But we didn't really look at how you might use co-await to chain tasks together. I think that discussion is better deferred to when we look at Boost Cobalt next month, because it's just going to be so much easier to chain things together and express ourselves at a higher level of concurrency using that library. Obviously, you can do it. They did it. But, why do things the hard way when you can do things the easy way? So that's the basics of coroutines. There's a bunch of videos on YouTube covering a lot more detail about the promise type and how you might choose different options, and how you might implement those customization points differently. But this covers the basics enough for us to understand what the Cobalt library is going to be doing for us when we look at that next month. If we have any questions, we'll stop for that. Otherwise, we will end it here. All right, no questions, so thank you.